So we all know what sorting is, but why is it important? Well, there are countless use cases from sorting files alphabetically to sorting polygons based on depth for 3D rendering, but many data structures are actually dependent on sorted data. Sorting also serves as a good introduction for runtimes and the thought process for these types of algorithms and data structures. Many sorting algorithms will be covered in this series, but I'll start with a very intuitive one, which is selection sort. Selection sort is very similar to a method for sorting that many people use when they're sorting things in real life. The basic idea is to continually look for the smallest value and put it in the front until you have everything sorted. This is for ascending sorts. If you wanted to do descending, you do the opposite, you look for the highest. Anyways, let's work out an example so you can see how it works. Let's start with an array of 5, 6, 1, and 12. We look for the lowest value, which in this case is 1. We find this by iterating over all the values and keeping track of the smallest value. After we found the smallest value, we swap it with the first value, which in our case is 5. After the swap, the resulting array ends up being 1, 6, 5, 12. You might wonder why 1 and 5 were swapped instead of simply taking out the 1 and putting it in front. This is because putting it in the front would mean you would have to shift many values by one slot. This is much slower than just swapping the values, and both methods would end up with the same result anyways. Now that we've determined the smallest value, we must find the second smallest value. We no longer consider the 1 since it's in the first slot, and we just considered the last 3 slots. In the last 3 slots, 5 happens to be the smallest. Since we're looking for the second smallest value, we swap 5 with the second value, which is 6. The first smallest value would be the 1 we found earlier. The array is now 1, 5, 6, and 12. We can visually see that this is sorted, but from the algorithm's perspective, we still have to check the last 2 values. Looking at the last 2 values, we see that 6 is smaller than 12. In practice, we take the 6 and swap it with the third value, which is also just the 6. So in effect, nothing happens and the array maintains the same order. Now that the algorithm has gone through the whole array, we know that it is sorted. Even though selection sort is intuitively what many people do in real life, it's actually a very slow sorting algorithm. For many values, you have to look at a large portion of the array. If you think about it for a bit, you'll see that the average amount of values checked for each time you get the smallest value is about half the size of the array. We have to find the smallest value for as many values as there are in the array minus 1. If the array length is n, this gives us our initial formula for big O as n minus 1 times 0.5 times n. As always, we drop the 1 since it's a lower term, and we drop the 0.5 since it's a coefficient. This gives us n times n, which results in a big O of n squared. This means that as we add more data to our array, the sorting gets exponentially slower. You'll see this in a bit when I demonstrate the code. For sorting algorithms, it's usually useful to consider the best case and the worst case runtimes based on the data given. For example, if the array is already sorted, some algorithms are O of n. However, selection sort does exactly the same steps regardless of what the input data is, so the average runtime is the same as the best and worst cases. Therefore, the best, average, and worst case runtimes for selection sort are O of n squared. Now that I've explained selection sort, let's get into how the code would work. I'll be using Python since pointers aren't taken advantage of in this algorithm. Alright, so I've got my IDE open here. The first thing we're going to need to do is just generate an array of values that we are going to sort. So I'm going to import random, and I'm going to create a function random list length. And when we want to generate a list of random integers based on that length, we'll do L equals random.randint -50 to 9999, so that just picks a value in that range for I in range length. So the reason it goes -50 is so that we have some negative values, because it's possible to make mistakes where you don't handle negative values properly, so it's good to throw those into your data set. So return L, and we can just do print random list, and let's get 10 random values and see what we get. Alright, it's a bit small down here, but you can see there's 10 random values down here. Now that we have a way to generate random values, we're going to want to write our sorting function, which in our case is going to be selection sort. In future videos, I'll cover other sorts, but I'll probably be using the same random function here. Anyway, so selection sort will take in a target list, and then for start I in range len target list. So it's just getting the array of every value in the target list. And then for every value, this is where you want to find the smallest value that occurs either as that value or after it, and swap that value with it. So we need to keep track of the lowest value seen. We do lowest I, so the index of the lowest value, equals start I, because as far as we know at this point from just looking at one value, that's the lowest value we've seen. So we just start from there. So for check I, so this is the values we're checking in range, start I plus 1, because you don't want to include the value we started at because that's already there. That's what we're going to be comparing against. So from the value after the first value until the end of the array, or in our case list, target list, if target list check I is less than target list lowest I. So basically, if you've just found a value that's smaller than what we thought was the lowest value, you say the lowest value's index equals the index of the value we just looked at. So this code right here just finds the smallest value that occurs after start I. So find smallest value that occurs after start I. And then after we have that smallest value, we can do target list start I, target list lowest I equals target list lowest I, target list start I. So this line is literally just swapping the values, or swap the lowest and the start value. And you have to remember that all this code is in a loop that's going over every single value in the array. So for every single value in the array, we're looking at all the values after it and then swapping with the lowest one. And as you move through the array and get to the end, you'll just slowly end up with a sorted array starting from the front. All right, so now that we've done our sort, we can return our target list. So if we do print selection sort, let's do it this way. So L equals random list. Let's take 10 values, print L, and let's do a selection sort on L. So we run it. I apologize, it's a bit small down here again, but you can see on the top we have our random values, and then on the bottom we have our sorted values. So something interesting to see here is how this slows down as you get faster. So let's start with like, let's do 3,000. Yeah, there we go. So you can start seeing some of these negative values that popped up in the front here because that's the sorted version. Anyways, so we have about half a second to do 3,000 values. So what happens if we do, let's do 6,000 values. So if you notice there, it went from about half a second to 2 seconds when I doubled the input. So if you think about big O and you see that you doubled the input and it took 4 times as long, that's a hint that you're dealing with something that is n squared. So let's double it again. Let's do 12,000. So based on the idea that this might be n squared, you would expect to see 2 times 4, which is 8 seconds. So as you can see, this was 7.5, which is pretty close to 8. So it's fairly safe to assume that this algorithm, just based on the runtimes we're seeing here, based on changing the input size, has a runtime of about O of n squared. And this is one of the reasons why it's not super important to fully understand how to derive runtimes by looking out an algorithm. you can just run the algorithm and change the input if you're mindful of how the algorithm works, because there are some exceptions for certain algorithms where you might accidentally run into best or worst runtimes. But if you know how the algorithm works, you can change the input and get a good sense for how it scales with more data. But if you think about this, this becomes a really slow algorithm if you add more data. So if I wanted to sort 120,000, I just made it 10 times larger, which should take like what, 100 times longer? I don't want to be waiting 700 or 800 seconds, which is over 10 minutes for it to sort 120,000 values. So there are better sorting methods than selection sort, and I will get into that later in this series. But for this video, we're working on selection sort. Before we move on, I'd like to demonstrate a way you can actually speed this up a little bit in Python. If you're not super fluent in Python, this might be a little bit confusing. I'm going to decrease this down to 3,000. So def selection sort fast, and we take the same target list, and then we do for start I in range len target list. So same thing as before. This is where it gets different though. You do check list equals target list start I and a colon. So this is kind of another way of breaking down the problem in a way that offloads the processing largely onto the C code that's running under the hood for Python. And this is actually something you have to keep in mind when you're working with interpreted languages. It's really good if you can optimize your code to use as much as the underlying functionality as possible instead of writing it yourself. In this case, we're looking at this problem as taking that part of the array that's after and including the starting value, and then finding the smallest value in that and swapping it with that first value in that subarray. So let's find the index of the lowest value. So lowest I equals check list.index is just finding the index of a value. Min check list. So you're finding the smallest value, and then you're finding the index of it. But this will return the index from checklist. We want to do the swapping since it's in place in the original target list, which means that we have to consider where checklist's index is with respect to target list, so we have to add start I. Don't worry if this is getting a little bit complicated. This is a bit more complicated to deal with because this is an optimization of selection sort for Python. It's still pretty much the exact same underlying algorithm. I'm just writing it in Python differently so it's faster. Now we do target list. Actually, we can just copy it from up here. You just do the swap based on the lowest index. And then you can return your target list. So let's take this and do selection sort fast. I'm going to copy L so we don't end up with any issues here. It's in place. So do the selection sort and the selection sort fast and make sure they're the same. You could actually do a comparison, but you can also just visually see that they're the same by just scrolling here. So I can just scroll to the end and see, yeah, this looks the exact same. So both these functions give the same result, but if you notice, let's take out this one. We run this, we get 0.55 seconds. We comment that out and do this one, the fast version, 0.2. Let's increase this to 10,000. So this one was 1.3 seconds. And if you remember from before, this one should be about like 6 seconds, 5 seconds. So you see how much of a difference there is there? This is just, it's a bit tangential, but it's very important to make use of the underlying functionality that runs faster when dealing with interpreted languages. And you may see me make use of this later on in this series when I deal with some other data structures and algorithms. And finally, just in case you're a bit unfamiliar with Python, this colon here is for list slicing. So I'm slicing out part of the list based on an index. So I'm just taking everything after that index and using it to create checklist. Anyways, that's pretty much all I wanted to cover for selection sort. In future videos, I'll cover some other types of sorts first before I go into other data structures and algorithms. One final topic that's a bit relevant is that you may remember Python has its own sort function, or sorted. They're sorted, and then you can do a dot sort on things. It goes two ways, but that sort uses something that's built into the Python interpreter, and that sort is called timsort. I believe it's named after the guy who made it. It's just a weird combination of two types of sorts that I will actually be covering in this series. So those two sorts are the insertion sort and the merge sort. Although the merge sort's the really important one here. Anyways, that's pretty much it for this video. Hopefully you guys will stick around and watch the next one. Thanks for watching.